So this talk is called The Functional Final Frontier. I sort of picked this curious title because I think that we understand that functional programming and programming oriented around values is really great when applied to many kinds of systems. A lot of the systems that you guys are building. One place where I think it's hard to see where this philosophy can be applied, or it's been hard to see, is actually user interfaces. So user interfaces came to being almost simultaneously with object-oriented programming. So for a long time, object-oriented programming and user interfaces have been almost synonymous. If you fire up a Smalltalk image today, there's an open source one called Squeak, which is pretty popular. And even though it's slightly different from the type of interfaces that we're used to on the desktop, you'll see a lot of familiar things. If you start inspecting the system, you're going to see that model, view, controller paradigm. This is still extremely popular today. It was first formulated by Trygve Reenskaug. Hopefully I spelled it and pronounced that correctly. Adil Goldberg and others at Xerox PARC in 1979. And it's had an extremely long shadow. The basic concept is still prevalent today. It doesn't matter if you're programming in Flash, JavaScript, C++, Cocoa, Android. MVC is just the way that people do user interfaces. And I think this is a case of good ideas eating their children. That's to paraphrase Alan Kay. I think MVC is a very interesting concept at a very abstract level. It is a sound separation of concerns. The main issue, I think, with it is that having been born out of the 70s when computational resources people were concerned about that, it was constructed on top of stateful objects. And that's basically true today. And I think that we can extract out the useful properties of MVC. At the same time, I think we can get rid of stateful objects. So funny enough, this is a screenshot of the NextStep OS, and this is the very first web browser. Tim Berners-Lee designed it using a very sophisticated object-oriented system, NextStep, using Project Builder and Interface Builder, which, as it turns out, were actually originally designed in Lisp and then ported to Objective-C. So I don't think Tim Berners-Lee knew that when he designed the basic sort of like network linked document model that this would be the primary way in the future that people would interact with computers. A lot of the things that we do with computers these days is online, and it's represented in the browser. Sadly, it's the document object model was never designed for doing the types of interfaces that people were doing with desktop toolkits, right? So I think a lot of people have this really deep loathing of client-side programming because you have this language called JavaScript, which was really meant for non-experts, on top of there's a plethora of MVC systems, which are stateful, on top of a DOM, which was never intended to even do this type of thing. So you often, to another Alan Kay analogy here, is that he often compares modern software architecture to building the pyramids. Yes, it's impressive, but it's just really brute force, right? There's not much of a concept here, right? Other than it's going to take a lot of people hundreds of years to do it. And he points out that really, that often what we need in software architecture is just a very simple concept, and that really allows for radically different architectures, and in this case, a much more efficient usage of architectural material. And that, and Alan Kay points out, that's kind of the arch, right? The arch was a great, simple architectural concept that had amazing potential. So I would argue that if you do a lot of object-oriented programming, user interface programming, I don't think there's been any significant advancement there as like how can we change the direction? Maybe functional programming has some ideas, and here's the big ones. You have functional reactive programming, which comes out of Haskell and the sort of pure functional programming community. It's very interesting. If you do sort of take the pure functional programming stance, it's still an open area of research as far as like how do we make it efficient and things like that. There are object-oriented variations of this. Reactive extensions is probably the one that's best known. But reactive extensions is very much a coordination language. They don't address the fact that you have to mutate something at the edges of your system, right? You have to render it. You have to render something. CSP, also, I think everybody here loves CSP. We like core async. But CSP is also a coordination language. It does not address the problem that at the edges you're going to have to mutate something. So are we out of luck? Is there no Arch? Is there no better sort of thing to build our user interfaces on? And I would actually say in the Clojure community, as well as for the greater sort of functional programming community, the answer has been lying right under our very noses, something that we use all the time. And that's persistent data structures. So I think for a long time in the Clojure community, it's been like 6 years in the Haskell community and Scala. Everybody understands the benefits of persistent data structures in the context of concurrent systems, right? It allows us to build highly concurrent systems and reason about them much more easily. But I hope to convince you that even in a single-threaded context, it's a better framework for building interactive experiences. Which leads us to this library that I started in December called Ohm. I've been working on it quite a bit, and people are starting to use it. And I'm just going to sort of give a sort of overview of the big ideas. I'm not going to talk too much today about implementation things. But basically, it marries the fantastic persistent data structures we have in Clojure and ClojureScript with React. And React is a rendering library from Facebook. And the big idea there is that they base everything on diffing. And as it turns out, taking persistent data structures and a diffing approach is actually an incredibly good combination. So before diving into that a bit, Ohm is very heavily influenced by the fact that I actually think there are lots of important lessons from traditional approaches. I actually think there are lots of great ideas, and the problem we're trying to solve is how can we keep the good ideas and ditch the bad ones? The other influence is I'm also a big fan now of Mathematica, and Mathematica sort of presents a type of UI that's where the data and the user are very close. There's not much distance between the data and the user. And so with Ohm, I want to accomplish two things at once. I wanted a system that could be applied to complex, rich interactions, but also would be a good substrate for more symbolic systems like Mathematica. OK, so there are four big ideas in Ohm. The first thing is immutable data. So what we'd like to do is we're just basically going to just throw stateful object out the window, right? Your entire app state is just a value D, right? And now we get to apply a function, and then we get another data structure, which is the view. And that's beautifully simple. If the data changes, you don't change the original thing. You just have a new value. You apply a function. You get a new view. And of course, the concern would be, well, how do you make that efficient? That problem is solved entirely by React. The calculation of the first view and the second view is done lazily. And what they do is they compute a diff between those two things that generates a list of changes, which they apply to the DOM for you. So you don't actually manipulate the DOM directly at all. What's beautiful about this, though, is like if we flip those arguments, right, that means we can get a reverse set of changes. So implicit in this model, you can go forwards and backwards in time just as efficiently. So maybe you're not convinced by that. Why diffs? Here's some more compelling reasons. So views re-render when the data changes. And this is awesome because that means there's no explicit observation. That means there's no resource issues, right? If you look at traditional MVC systems, you have people binding models to controllers to views. Every time you add a listener, right, that's a resource. A very common source of error in JavaScript is you add a listener to the DOM, and then you mutate the DOM or blow that thing away. And that's a memory leak, right? So the React model tries to eliminate the sort of resource issue that occurs with explicit observation. This is true for example, for Rx, right? You have to, it's a resource if you start observing something. And again, this just means a lot less logic to write around observation and view updates. There's just a direct correspondence. If the data changes, the view changes. So real quick, I did a blog post about Ohm in December, and caused quite a splash because I think people were shocked by the fact that ClojureScript, which is compiled to JavaScript using slower data structures, was faster than Backbone at rendering a simple benchmark. Right? It actually turns out that Ohm is actually faster than React because we implemented a well. Oh, it's just out of the box. It's faster than React out of the box because we pick a better strategy and we know when things change. And in JavaScript, you don't because people are using JavaScript objects and you can't efficiently detect changes. So that's pretty cool. So, but just to show a concrete example of why representing your app state as a persistent data structure is nice, is that this is, I wrote 5 lines of code to do undo, for example. So here's a user interface. I'm writing some things. I change that, go like this, click this, delete that, click, right. So I had to do no work to make this work, right? This is just falls completely out of diffing and immutable data, which is pretty cool, right? Undo is actually traditionally extremely hard to do in a traditional MVC setting. OK. So the question you should be asking yourself then, if we're going to do this global app state thing, what are we going to do about the problem of modularity? If we really take this database approach, something that people like about objects is that they're sort of naturally modular. And that's because I actually think objects sort of complete encapsulation. This, this is a big idea in objects, is that you hide your state. But I actually think that's basically complecting the fact that we're getting modularity, but really for this bad idea, which is hiding state. And I actually argue that objects are not actually modular with respect to state because of this reason. So what we'd like to do is we want to keep the modularity of objects, but we're going to absolutely throw this hidden state thing out the window. And by doing this, we'll get modularity with respect to state. And to make this a little bit more concrete, imagine we have some UI and we have some root component widget thing, and it has three components under it. And somebody says, oh, I have a really great widget that has this extra stuff. And in a modular system, you should be able to swap out widget A with widget B, and it just works. And imagine I'm working on this project, and I want to swap that new widget in because it satisfies the right interfaces, and then it doesn't work. And why doesn't it work? Because there was hidden state inside that thing. If you do a lot of Java, this is like a common case of this is like, is your object thread safe? It doesn't matter if the state is hidden, right? There's a state strategy that's implicit in the way you design your objects. Encapsulation doesn't matter. In a single-threaded context, you could think about undo, right? So I have some widget, and I want to use it, and I want to implement undo in a global way. But if your component hides its state, I can't integrate your thing, right? So your state strategy affects the modularity of that component. And this is something that will drive you crazy. So Ohm is very much based on the way React works, the way that Clojure works. But it's also based on a little bit on, there's this guy who's kind of wild, David Barber, but he wrote this really great blog post called Local State is Poison. And this is something that I think Ohm definitely in many ways embraces. So we have a global app state. It's an immutable tree of associative data. It is global state. Again, it's not as scary as it sounds. We all program against databases. Databases are also global mutable state. The only question is, how can we recover component modularity? How can we get sort of a local view on the data such that our widget only sees the part that it needs to see? So this is the only part where I'm going to talk about the implementation. You could imagine alternate implementations. And actually, the implementation that's in Ohm is like my third attempt at getting modularity in the presence of a global app state. And so I invented this thing called cursors. It's very close to zippers and to some degree functional lenses. But basically, a cursor is simply a wrapper around one of the ClojureScript collections, right? It provides exactly the same API as the collection, but what it does internally is it's a triple. It's a consistent snapshot of your app plus a path, like where does that data live in the global app state, and it's a reference to the global app state in Atom in Ohm, so that a component can update the part of the app state that it cares about. And what we do is we track the path via normal collection access patterns. And this is way more, I find it way more simpler to understand than zippers. Zippers provide this API that's like up, down, left, right, and that I think is not the way we want to program UIs. So making this a bit more concrete, this is an example OMAP, or a piece of an example OMAP. And you have, a tree of associative data, some nested maps, nested vector. And we want to render some widget, some view. We give it the app state, and we replace some element in the DOM. Now, what some view is going to get is not that data. It's going to get a cursor over that data. And you notice when it starts, it's just the original data. The path is empty. And then we have a reference to the state. So if this component needs to update the application state, it can. Down here, we access the foo key in that cursor. And we're going to get back a new cursor, which has the piece of data that is at that key. We update the path. And then again, this is the same state reference, so that if somebody needs to update the value at that path, they can. We can imagine further down that we invoke some subcomponent, and we access more deeply into that cursor. And then another view will get just the part of the app state that it needs to know about. So the path, by tracking the path, components never actually know where their data comes from, right? They don't need to know where the data exists inside the global application state. And this allows us to have global app state, yet have modular components at the same time. So this is just the beginning. This is a good foundation, but I think for the types of UIs that we want to build, it's actually not quite enough. And so I want to talk about 3 other things that I think sort of complete the story. So when you're building a UI, you have something simple, and then you realize, oh, I need to sort of customize a component, but at some sort of higher level. So I might have some component, I want to customize it with a function f, or another component, I want to customize it with a function g. Another component, customize it with a function h. So Ohm actually provides this capability via something called instrument, because I think this is too common a pattern. It's very much an aspect-oriented programming idea. It's a tasteful application of global concerns. So when you're designing a component, you don't care about the rest of the world. You just care about, is this a reusable component? I don't really care how other things in my system work. However, when you're building applications, you often have global application concerns. If you ever look at a serious MVC framework, there's some way to talk about global concerns, right? Because when you're architecting an application, it's just very common that you have something that you want to apply to the entire app. So basically, instrument lets you intercept the construction of any component. So you get to receive all the parameters, do something else, including re-rendering the original thing if you like. This gives us generic editors. There's actually tons of possibilities here. For example, if you're familiar with Mathematica, it's basically the hook you need to do manipulate. I just want to show the generic editor case, because that's pretty cool, I think. So here we have, oops, sorry. So here we have, this is an Ohm component, and it has 3 subcomponents. And then what we're doing is down here, we're actually rendering it again. This thing down here is actually exactly the same thing. The only difference is that we used instrument to intercept those components and to create a generic editor around it. So if I'm clicking here, you notice that it's obviously the same thing because they're completely in sync. If I have this little text editor, and there's the Eden that backs this, and I can, right? So there's, again, we were seeing how, wow, we were able to do this sort of object-oriented thing. We're able to do this sort of Mathematica direct manipulation thing. And all instrument is just a function, right? It's just a function that's going to receive every component. You can pattern match on it. You can unify on that. It doesn't matter. But this is a hook so that if we want to build it allows kind of a whole universe of meta components. And we'll actually see somebody's actually using this to build something pretty cool, which I'll show later. So the third thing I think is really important when you're building UIs is communication. How do components communicate with each other? Actually, I think core async solves most of these problems. There is one thing that it doesn't directly solve that Ohm can provide that I think is really useful, and it's this feature called TX Listen. So now that we have a global application state, it's possible to always be aware of any change to the application, right? And in fact, some component might want to subscribe to a particular type of change. One specific use case that I had in mind when I did this was that while persistent data structures in memory are great for traveling back and forth in time in memory, it's really a horrible serialization format, right? You don't want to have to like serialize snapshots over and over again. So txlisten is a way to get to subscribe to the deltas. It'll give you the path that changed and the old and new value. And that's something that can be efficiently serialized to local storage or synchronized with the server. And I think that's pretty useful. It also means that you can do something that's like kind of like very difficult to do is what I would refer to as generic controllers. I actually think components that ship with synchronization logic in them is completely an anti-pattern, right? Because you then have to assume that the way that it's done is the way it's always going to be done, right? They've hard-coded a synchronization strategy in. Whereas with txlisten, what you can do is just say the synchronization strategy is a reusable thing. It doesn't matter what component it's looking for a listening at. So you can build basically reusable controllers. This is something that's not true in most MVC systems. And the last bit I want to talk about is, I think I showed this slide on like literally every talk I do. Protocols are really important. And it's important to pick a good set of protocols. I think Clojure and ClojureScript are very inspiring in this way, that most of the abstractions are tweakable. So Ohm has protocols for all of the fundamental operations that it allows. So for example, I thought for me, most user interfaces can get along with just the associative data structures. But for example, you might want it to work on sequential or whatever, and we'll see how this can be done. So you can make cursors work for more data types, for your custom types. But even more importantly, you can redefine the semantics of state change operations, right? So this is extremely critical because when I started working on Ohm, I realized, well, I don't really want Ohm. I don't want people to build amazing Ohm components that then you only can use with Ohm. That doesn't make any sense at all, right? So you can actually reprogram the way state works. So for example, if you want to use an Ohm component in React, or you want to use it in Reagent or Quiescent or any of these other React-based libraries, it's actually trivial now to make Ohm components work outside of all these other optimizations that are in place in Ohm itself. The other thing it lets you do, it also lets you eliminate hidden state. If somebody gives you a component and you want to force it to work with your undo system, you can actually force that component. Like, we actually support setting component local state for performance reasons. But I realize that sometimes you want more control over the component you're given. So you can force that component to write its local state into global state. So, for example, that you can make it work with whatever undo strategy that you have. And this means that components are just more adaptable, right? Any component that anybody gives me, I can change those semantics so that it works in my situation. And that means they're more reusable. I actually think adaptable is far more important than reusable, because I think it's a level beyond reusable. So you take these four big ideas, the global app state, instrument, txlisten, and the fact that it's all built on protocols, then a lot of things are not only simple, but they're also easy, right? We definitely want to prioritize simple, but it's great when things are simple and easy. So undo, redo, time travel, simple to do, it's easy to implement. Meta components, because of instrument and it presents such a simple API, really easy to do as well, and simple. Synchronization online, offline, again, simple and easy to implement. And then Ohm components play well with others. Ohm is not like an island in the world of systems that want to use React as the renderer. So I just want to end with some demos that are not my own. People have been doing some pretty cool stuff. And hopefully this demonstrates that you can do both, again, like the sort of like traditional MVC type application, but you can also build symbolic systems like Mathematica with Ohm without any difficulties, because we don't assume how you want to architect your UI. So the first example is an interface builder-like thing by Sean Grove, who's here, and I think he's going to be doing an unsession later today. And so I'm going to show a video of his, of something he's working on called ZenRise. So this is, he's actually using reusable Ohm components to make a generic editor for Ohm apps. Like, this is a basically interface builder for Ohm. So on the right side, you have drag and droppable components. You have the app state right here. So if we I want to play this from right about here. So you can drag and drop, horizontal split views, text views, whatever. The app state is on the left, and what he's going to demonstrate here is that he can say, this is how my UI components are bound, and it's going to generate data such that you can basically build with an interface your declarative UI. So he's binding the app state to something in the UI right there, which is pretty awesome. This is a very early prototype, but I'm impressed how far he's taken it. If we scroll to the end, you can see that so in 15 minutes, he has the basics of a chat app. And he completely built it interactively, which is amazing. And this is a functional interface builder, right? OK, the other example I want to show is the sort of more mathematical-like example. So today, Kovas Boguta, who's a good friend of mine, released Session. Session is a new kind of REPL. It's backed by Datomic. It's completely built on top of Ohm for the front end. And I'll show a quick demo of that. So here we have an interactive REPL. He's added a lot of features. So if, you can type expressions here. I can do this. It has graphics. You can style that. Where it gets cool is that you can embed graphics inside of vectors. Right, so this is actually a vector that contains graphics primitives. So if you're used to Mathematica, this won't impress you at all, but I think this is pretty cool. It's all based on Eden. It's extensible. If people want to add new components, they can. It just works. Of course, being backed by Datomic, you get a lot of nice properties like undo, redo. You're able to query your REPL history using Datomic data log syntax, like he has right here. I think that's pretty awesome. But that's actually all I had. So I think I'll take questions now.